Hello, everyone. In this particular video, we're going to talk about generalizing the idea of projections, but this time not projections upon a line or a vector, but rather a projection upon an entire subspace of Rn. It's not very difficult, actually, but it does take us quite a while to get to the end result. But in the end, it's very similar to things you already know. So far, the way I've introduced projections is a projection upon a single vector. And in the previous lessons, just previously, I showed you how to go and use projections to express a single vector as a linear combination of two vectors that span a space, or three vectors that span a space. For example, to remind you the idea is, if you have a plane and you have two vectors that form an orthogonal basis for that plane, so we'll call those vector u1 and u2, and you have another vector in that plane, let's say v, you can then write v by going and finding v, its projection upon these separate vectors, u1 and u2, and v then would actually have to be the sum of those two projections. So that's a quick result I gave you last class or last lecture when we talked about orthogonal bases. I want to take this idea and extend it to vectors that are not in the plane but out of them also, to see how it relates to these different projections. To do that, though, I need to introduce a new concept. So if you have a subspace of Rn, let's say that subspace is called W, a vector V is called orthogonal to that subspace W if it's orthogonal to every vector in W. The set of all vectors orthogonal to a subspace is called the orthogonal complement of that subspace, and it's denoted with W with like a perpendicular symbol, and it's said or spoken as W perp. So I want to give you an idea what the picture kind of looks like, so you have an idea of the relationship between W and W perp. I drew a plane, so W is a plane that passes through the origin. It's therefore a subspace. If I wanted to know what was the orthogonal complement, it would be all the vectors orthogonal to that plane. And if you put them all together in one direction, actually starting at the same spot at the origin, you make a line. So then the orthogonal complement to a plane should be a line. And I just wrote down the notation here to show you the relationships between things. So W perp is just all the vectors in Rn, so that this vector is orthogonal to every vector in W. Okay. Now there's some basic properties about this new thing, this new set of vectors, W perp, that you need to know about. First off, and one of the more interesting things, is that if W is a subspace, well, then W perp is also a subspace. It's just a subspace of a different thing, like Rn, Rm, something else. Oh, well, in this, actually, sorry, it's also in same, they're both in Rn. Also, the orthogonal complement of the orthogonal complement, so W perp, is actually W again. They undo each other. That's only true, by the way, if W is a subspace. So if it's not a subspace, then actually you can figure out what W perp would be, and it's actually usually more than W. It's actually more than W. Next, if you look at the subspace W and you look at the subspace W perp and take their intersection, that's always the zero vector. They absolutely have nothing in common other than the zero vector. That's a really, really useful fact. And then lastly, if you have that a subspace is spanned by a bunch of vectors, then you can show that a vector is in W perp by just showing you that every single vector, that vector V, is orthogonal to every vector that spans W, and vice versa. So that if a vector is in W perp, well, then it must be orthogonal to every vector that spans the space. Most of these things are really easy to prove. It's just a matter of just kind of writing down notation and being careful. I'll do one of them right now, A. Many of these you'll do on your own. B is something that we can actually prove it towards the end of this lecture that I'm just not bothering doing. C and D are both very easy and are actually part of the homework, I believe. And I'll explain C and D really quickly, notationally. So then for this one, what if you had a vector that was in both? So what if there was a vector that was in W and was also in W perp? Well, that means that if you take their dot product, of that vector with itself, that's got to be 0. Because if it's in W and W perp, it's a vector that's orthogonal to itself. It has to be. That's what it means. But the only vector whose dot product with itself is 0 is the 0 vector. And that's it. That's the whole proof. It's very straightforward. The other one is also really pretty easy. If, let's suppose that V is in W perp. So then if V is in W perp, it's orthogonal to every single vector in W. Well, but W is a span of a bunch of vectors. So that means automatically that V must be orthogonal to W1, and it must be orthogonal to W2, and so on. Automatically that happens. So one direction is very easily done. In the other direction, if we had that V, its dot product with every one of these WIs, if that's always 0, that means then that if you take V and take its dot product with any linear combination of them, C1, W1, up to CK, WK, by the properties of dot products, that has to be 0 also, because the dot product distributes with everything, and then it distributes through the scalar multiplications. You would then have V dot with W1, which is 0, V dot with W2, which is 0. That means then that V, its dot product with any linear combination of the W's would be 0. Therefore, V is orthogonal to every vector in the span of those vectors. Therefore, V is in W perp, right? Because it's orthogonal to every vector in W. Easy. These are, again, very straightforward. Just extensions of ideas you pretty much already know. Let's not look at these anymore. Let's move on. So this proof, though, is important enough that you really should see it written out very carefully. It's not difficult, again. It's just a matter of looking at things carefully and remembering what notation means. Let's suppose that W is a subspace. Then W perp is also automatically a subspace of the same space, Rn. The proof of which is really easy. Remember, to show that something's a subspace, there's 3 things. You have to show that the 0 vector's in it. You have to show that if you have 2 vectors in it and you add them, it's still in the space. And then if you take a scalar and a vector in that space, the scalar multiplication is back in the space. I'll show you how to do all of them really quickly. So then notice, though, that 0 dot with W is just 0. So automatically the 0 vector is in W perp, because 0 is orthogonal, its dot product is 0 with everything. So it's automatically in. The next one, I'll just do both the vector addition and scalar multiplication all at once. So suppose you have 2 vectors in this W perp and C is any scalar. Then if you add the vectors and take the dot product, we know that when you add these vectors and take the dot product just distributes through. But the whole point of this vector W, or this whole point of this vector U and V, is that they're in W perp, which means the dot product of U with whatever W is 0, and the dot product of V with any vector in W, that's 0. So that dot product is 0. Also, if you take any scalar of U and multiply it and take its dot product with any vector in W, the scalar can come out. You would then have the dot product of the vector U in W perp with some vector in W. So that dot product is 0. So you have 0 times the scalar, which is just 0. This means then for every single vector W, every vector in W, U plus V is orthogonal to it, and C times U is orthogonal to it. So that means then that U plus V is in W perp, and C times U is in W perp. So therefore, this particular set of vectors, W perp, satisfies the 3 conditions we need to be called of subspace. And I think that's enough for this video.